Good afternoon, class. We are actually finished the all the formal lecture in Thermal 1 this semester. So for the remaining time, I'm just going to talk through these homework problems, the solutions of which I have already sent you. So you can pull these up, your own copy, or you can watch on the screen here. This is problem 1018, which was assigned in the first batch. So we have a vapor compression refrigeration system. It has a capacity of 10 tons using R134A as the working fluid. We've got data and a diagram of the cycle provided below we'll look at in a second. And this is nice. They provide the thermodynamic states and property data to you as well. Compression process is internally reversible and can be modeled as a polytropic process. Pressure times specific volume raised to the 1.01 power is equal to a constant. Condenser is water cooled. That's a little bit different for us. With water entering and leaving with negligible change in pressure. So we don't have any pressure drop across the condenser. Heat transfer from the outside of the condenser can be neglected. So the energy from the refrigerant goes directly to the water through the heat exchanger. Determine the following. You say all that stuff: mass flow rate, power input, heat transfer rate for the compressor. So we're going to calculate a heat transfer rate from the compressor, each in kW. The COP, coefficient of performance, mass flow rate of cooling water, kilograms per second. We'll do E, the entropy production in the condenser and expansion valve, and kW per degree K. And we can't do F. We haven't done the exergy chapter. I think you get that in Thermo 2 these days. So we skipped that part. So we won't do F. Okay, so this is just restating and restating. So here are the states. 1, 2, 3, 4, 5, 6, and the engineering model, control volume, steady state, polytropic process within equals 1.01. Expansion valve is the throttling process. Heat transfer from the outside of the condenser is neglected. Kinetic potential energy effects are negligible. And this T0, that's tied up in the exergy calculation, which we're not going to worry about. Okay, so here's all of my state points. So we pick up two more, and those are just the cooling water coming in at 20 degrees C and leaving at 30 degrees C. That's where the heat's being rejected. Instead of to the air, it's just going to the cooling water this time. Okay, so, the evaporator, we've got one we're showing superheated over here. Coming into the compressor. And this is our polytropic process from 1 to 2. And then we condense from 2 down to 3. 3 is a little subcooled. And then 3 to 4 is constant enthalpy down to the low pressure side of the system at 4 bar. And we have the temperatures listed over here. And then we've got all the state points information in the table, which we'll refer back to. Okay, so let's start out with A. The mass flow rate is found using the refrigeration capacity. So our absolute number that we have for the system is 10 tons of capacity, and so that's Q dot N. Well, that's got to be equal to the mass flow rate times the enthalpy difference, 4 to 1, because that's the cooling effect. So that's where the 10 tons of cooling would occur. So that's pretty straightforward. So we got our 10 tons, and then we have to, let me see, I got to put this on hold for a second. Okay, so we've got our 10 tons of cooling capacity, and this is the definition of a ton of cooling in the metric system, 211 kilojoules per minute per ton. And then we want to get it to kW, which is, so we have to go to seconds, or we're going to do this in kilograms per second. Later on, we do some kW stuff. And then just divide it by the enthalpy difference across the evaporator, which would be H1 minus H4 right here. And so we get our mass flow rate has to be 0.241 kilograms a second. Okay. So then we move on to B, which is to determine the compressor work input. And this expression for polytropic work was developed previously. The integration was done. This is in the chapter. You can go back and look at it. But anyway, doing that integral, we get the exponent n divided by n minus 1 times P2 specific volume 2 minus P1 specific volume 1. That'll give us the work, the specific work, rate of doing work, or the power per unit mass. And so just plugging in, n is 1.01 divided by 0.01. And then let's see, so yeah, this is P2, V2 minus P1, V1, and then with the conversion factors. So we're coming out at 12 bar, we're going in at 4 bar, specific volumes just out of the table already developed for us. And then we have to juggle our units. That's probably the hardest part of this, and looking up this equation, or doing the integral. I guess you could do that. With the conversion factors, we come out with 23.432 kilojoules per kilogram. So for every kilogram through the compressor, that's the amount of work, kilojoules of work that we have to do. And then if we want the total, then we multiply it by the mass flow rate. And so we've got our 23.432 kilojoules per kilogram times 0.214 kilograms a second. And then that's going to be kilojoules per second, but that's the definition of a kW. And so we've got 5.647 kW of total work input. That's the rate of work going into the compressor. And so we do an energy balance. That's actually going to be a negative, right? Because that's being done by the machine on the working fluid. Okay, so the heat transfer, yeah. Let's see. So we have solved for the heat the first law of energy balance. And so we've got Q is equal to minus the work of the control volume plus m dot delta H. And so plugging into this, we see that, so this is plugged in as a negative. And so we have the minus 5.647 kW. And then the mass flow rate times the enthalpy difference across the compressor from 1 to 2. And so plugging in the numbers, we get minus 0. These pop-ups are killing me. Minus 0.0606 kW. Okay, so that's the heat transfer rate from the compressor. Okay, and then the coefficient of performance is just the Q dot N, where we're given the capacity and then divided by the compressor work. And so we just have to get it in the same units. And so all of this, the 60 well, the 211 is kilojoules per minute, so we got to get kilojoules per second, which is kW, and so we have the compressor work in kW. So when you do all that arithmetic, you get 6.227 as the coefficient of performance. And then this is asking for the rate of the cooling water flow. And so we've got this stream at 2 is hot, at 3 is cold. And so all that decrease in energy is going into the cooling water. So we can just do an energy balance around the condenser. And let's see, so that's what we're doing here. So this is the mass flow rate of the refrigerant times, it comes in hot at 2, goes out cool at 3. So, and then that has to equal or balance in the mass flow rate of the cooling water times the enthalpy difference across that. So we're writing this as a positive. So this one's going to be a negative because they're on the same side of the equation and they have to add to 0. So they're really equal to each other. One's in this sense positive, negative, or you can move this to the other side and flip the signs, however you want to think about it. But we know the enthalpies. And so solving for the mass flow rate of cooling water, we simply would take this, probably take this one to the other side so that we get H6 minus H5, and then divide through by it. So we get the mass flow rate of the cooling water as mass flow rate of refrigerant times the quantity H2 minus H3 divided by H6 minus H5. Plugging in the numbers, we get 0.9743 kilograms per second. Okay. And then for the rate of entropy production, it's a throwback to a previous chapter, right? That's not hardly fair. This is dsCV/dt, so we're not, nothing's changing with time. So then this is the entropy transfer due to heat transfer. And we're looking at the condenser, but we don't have any heat transfer from the exterior surface. All of it is internal. And so we just have the flow terms up here. And so that's the mass flow rate of the, that's the refrigerant times coming in is 2, leaving is 3, plus the mass flow rate of the water coming in is 5 and leaving is 6, I believe. Coming in at 5, leaving is 6. Right. So that looks to be correct. Plus the entropy production term for the condenser, and that's what we really want to solve for. So we're going to leave this over here and take everything else to the other side of the equation. So that just switches. We take the negative sign into the parentheses. So the S2 minus S3 over here switches to S3 minus S2. And the S5 minus X6 on the other side of the equation is S6 minus S5. Plugging in all the values, pretty straightforward. We get 0.00924 kW per degree K. So that's not too bad. And then we do the same thing for the expansion valve. There is no heat transfer. And so it's just the mass flow rate and times the entropy difference. And so it's already been taken to the other side of the equation. So it's S4 minus S3, plug it in, and we get 0.003003 kW per degree K. So that's it. We're not doing F. So that's the end of problem 18. Okay, so we're on to problem 1025. And this is kind of an interesting system. Ammonia is the working fluid in a 2-stage vapor compression refrigeration system using a direct contact heat exchanger to achieve intercooling. Data for the various at the various locations and the refrigeration capacity is given. We'll see on the diagram. So we want to determine all of these things, and we'll get to those one at a time. But here's our diagram. So we see down here at the bottom, Q dot N is 30 tons. So that's the capacity of our system. Occurs at the evaporator. We just have two stages of compression, and this direct contact heat exchanger serves as air cooling to do some cooling on the discharge at 2 before it goes into the second stage of compression. That cooling helps the efficiency of the system or enhances the COP, however you want to think about it. And then the heat rejection is from the condenser up here. And we have 2 expansion valves and 2 compressors. And so this is what the schematic and the TS diagram look like. So I don't know, start someplace. Start down here at 1. So we see we have saturated vapor coming out of the evaporator at minus 20 Fahrenheit. So we can look up that pressure from the ammonia tables. And so we have a real compressor. It's not isentropic. We show the isentropic point as 2S, and then we show the actual point at 2. And so it's going to pump it up to 80 psi at 0.2. And then we're going to come in here with our, this will be superheated vapor for sure. And then we mix coming off of the expansion valve over here. So this would be at, let's see, well, this will be back at 80, because so when we come through this expansion, we're going to pump it up to 250, but we condense it, but it's going to come back over here. So this will be a 2-phase mixture coming in at 6, which we show right here. And so we mix 2 comes in and 6 comes in. And so then we take vapor out at 3, which goes to the second stage of compression. So that's a saturated vapor we're assuming. And then we have saturated liquid at 7 coming through this second expansion valve. A little bit complicated. The compressor efficiencies, isentropic efficiencies are 0.85 each. So we'll have to take that into consideration. So then we come out of the second compressor at 4. So we're over here at the real state, not the isentropic state. And then we just condense to 5, rejecting heat to the environment to get us to saturated liquid at 250. And then we're going to go through that constant enthalpy from 5 to 6. And so we get some vapor, and the rest is liquid at 80 psia. And then, like we've already said, the liquid falls at the bottom at 7 and goes through another expansion valve to 8, which again is a 2-phase mixture. More liquid, but there is some vapor in it at 8, and then that goes in the evaporator and gets evaporated to get us back to 1. So pretty interesting cycle, I guess. Okay, so you can read the model. It's our standard stuff. So let's say, first thing we have to do is we have to go, and he's going step by step, finding all of the properties. So for example, at state 1, it's minus 20 and it's saturated vapor. So you go to the ammonia, saturated ammonia table at minus 20, and you can just read an entropy and an enthalpy. Enthalpy is 604.61 BTUs per pound, and the entropy is 1.3762 BTUs per pound per degree Rankine. Okay, and then from 1 to 2, that's an isentropic compression, so we're going straight up. So here we know our pressure and the entropy at 2s is the same as the entropy at 1. So we have to go and do some interpolation to find 2s in the superheat tables. So you should verify that you can do that. So 692.14 is the isentropic, and then this is the expression for the isentropic efficiency. It's H2S minus H1 over H2 minus H1. So we're going to solve this for H2, which we've done here. And then when you plug the numbers in, you get 707.59. Okay, and so that moves us then along to state 3, which is saturated vapor at 80 pounds per square inch absolute. So that's a straight lookup from the table. So that's pretty easy. That's at 3. So we get 623.32 for the enthalpy and 1.2529 for the entropy. We go through the same process. We go straight up to state from 3 to 4s. So here we know the entropy at 4s is the entropy at 3. We know the pressure. So we're back interpolating in the tables to find H4s. So 693.53. And then we use the same equation based on the isentropic efficiency of the compressor. And so the actual enthalpy at 4 is 705.92. Okay. 6 is saturated liquid. That's coming out of the condenser at 250 pounds per square inch absolute. So that's a straight lookup in the table. Enthalpy at 5 is 167.77. And so from 5 to 6 is a throttling process. So we have the same enthalpy at 6 as we have 5. And then let's see, at 7, what are we doing at 7? At 7, we're saturated liquid coming out of the bottom of this direct contact heat exchanger at 80 pounds per square inch absolute. So that's a pretty easy lookup. So that's 7, so 91.22, and 8 is the same enthalpy because it's a throttling process. So from 7 to 8 is constant entropy. I'm sorry, enthalpy. Okay, so now we start solving for things. We're going to solve for the mass flow rate through the evaporator because that's where we know it's 30 tons of capacity. And so that has to equal the mass flow rate times the enthalpy difference of the refrigerant out minus in. So that's pretty simple. Solve for the mass flow rate at 1, 30 tons, changing units. A ton is what, 200 BTUs per minute. And so there's the enthalpy difference. So we get 11.69 pounds per minute for the flow rate out of that. Pretty straightforward. So the mass flow rate into the second turbine stage is determined by using an energy balance on the direct contact heat exchanger. So summation of the mass times enthalpy in is equal to summation of mass times enthalpy out. So what do we got? We're coming in at 2, we're coming in at 6, we're leaving at 3, and we're leaving at 7. So we should be able to see that. Coming in at 6, so m dot 6 times h6. Coming in at 2, m dot 2 times h2. Leaving at 3 and 7, so minus m dot 3 h3 minus m dot 7 h7. And we know that m dot 6 has to equal m dot 3. Let's take a look at that. Say m dot 6, what comes down through here? Well, how did it get there? It came through over here. So it's the same mass flow because we're steady state. And we know that m dot 7 is equal to m dot 2 is equal to m dot 1. So let's go back and look at that. M dot 7 is equal to m dot 8 is equal to m dot 1 is equal to m dot 2 because that's the same flow rate through there. Okay. So making all those substitutions, we can solve for m dot 3. And we do that in terms of the enthalpies, and we plug in the numbers, and we get the mass flow rate at 3 is 15.82 pounds mass per minute. So the first thing that you wanted to calculate was this ratio, m.3 to m.1, 1.353 is the answer. Just plugging in this and the 11.69. Okay. So then the power input to the first compressor stage is just the mass flow rate times the enthalpy difference. And so this is the actual enthalpy exiting, not the isentropic. So we're plugging these numbers in, and we have a conversion factor over here. Horsepower is 2545 BTUs per hour. And so plugging that in, we get 28.38 horsepower. And the power input for the second compressor stage is its mass flow rate times its enthalpy difference, and then converted, because that's right, we have a 60. Yeah, we got to have a 60 because we've got pounds mass per minute, so that makes it hours, and then we convert it. So it's basically the same calculation with different numbers for the second compressor. So we get 30.81 horsepower, and the coefficient of performance is the 30 tons divided by the sum of the two compressor work inputs. And of course, we got to get that, we got to get these in the same units. This is horsepower and this is tons. And so we have to do some conversions. So what are we going to do? We're going to get rid of the horsepower. So 1 horsepower is 2545 BTUs per hour. And then we're going to get rid of the tons. So a ton is 200 BTUs per minute per ton. That gets rid of tons. This one gets rid of horsepower. And then we got to convert because we got what, BTUs per minute, and we got BTUs per hour, so that'll never work. So we got to get rid of one of them. So we multiply by 60 to get rid of the minutes. So everything becomes dimensionless, and the coefficient of performance is 2.39. Okay, and then D has to do with their software. We haven't used their software, so we're not gonna do that.